Thank you. Yeah. So we had the question about, now that we learned how to evolve the quantum state in time, how does that help us calculate the properties we want to calculate? Right, because they said just taking a state, I want to evolve it in time and the Hamiltonian. So how do we actually get to, for example, the ground state of a system? And one approach that you can do is just adiabatic state preparation. And that works like the quantum annealer. I start at the time t equal for 0 in the ground state of some Hamiltonian h of 0 that I know how to prepare. And then I evolve under a time-dependent Hamiltonian h of t until at some time capital T, I'm in the ground state of h of t. The problem here is what do I choose as the starting one? Because when I go through a phase transition, from that, if going from 0 to there, I pass through a phase transition, then the gap closes. If it's a second order the phase transition, it goes with the power law. When first order, then the gap becomes exponentially small. So what I do there in practice, or what I will do on a quantum computer in practice once I have one, is I would start with the different mean field Hamiltonians, which I assume are in the possible phases of the ground state. For example, in the Hubbard model, I could start in the magnetic phase. I could start in the density wave ordered phase. I could start in the conducting phase. I start in the mean field model and the mean field ground state and evolve. And if I guess the right phase, then the gap doesn't close and it goes very fast and very well, and it's easy. But how do I know which of these states is the best? The superconducting or the stripe ordered phase or the magnetic phase? How do we know which of these approaches, which of the paths we took was the best? Any idea? I start in the mean field state of the superconducting Hamiltonian, just assuming that's the broken order, and I evolve my Hubbard model from the mean field state to the full Hubbard model, and then I hope to be in the ground state of the Hubbard model if it was superconducting. One may start from a magnetically ordered state, or the density wave state, and evolve. And have some the phase diagram that might somewhere include the superconductor, the antiferromagnet, the density wave phase, and more. And they start always from the mean field from the mean field points, and they evolve under the adiabatic evolution. Let's assume the true ground state is here, and this path goes well. The gap never closes. It's fine. This path here has a problem at phase transition, but maybe this path even goes through it like that, through two phase transitions. but I then want to find out which of those should I trust. I can start from here, here, or here, and I evolve. When I do these with the gap closing rapidly, maybe there's a problem. How to detect that? I could then measure correlation functions when I then compare, but how do I know which approach was the best? If we don't know where the phase transition line here is. I check the energy, yes. How would I check the energy? I can, so when I have the Hubbard model, I could just measure the expectation value of every single term that appears in the Hamiltonian, measure that. Then I sum up the terms and I get the energy, and I check which of these states gives me the lower energy. But there's a better way of doing that. So what I would do at the end is, I would say what I have there is a good enough trial state, and now I want to actually project into an eigenstate by measuring the energy coherently. So what I want to do is I want to do quantum phase estimation to project into an energy eigenstate. Who has not heard of quantum phase estimation, or have you all heard about it? So quite a few. That's good. So the basic idea is, if I have a Hamiltonian and a wave function, if I can measure the energy projectively, then the wave function collapses into one of the energy eigenstates. But how do I measure it? I can't just measure, for example, the U term and the T term separately, because then it goes into an eigenstate of the U term and the T term. So I have to measure the total energy. And the way I can do that, I can take a wave function, and let's assume I'm in an eigenstate psi, and I evolve in time under the Hamiltonian. Then if that's an eigenstate, then all I pick up a phase that is just the energy minus I e t times the wave function psi. So if I can measure the phase here, that gives me the energy. If this was not an eigenstate, by measuring the phase, I collapse into an eigenstate. And if that state has a big overlap with the ground state, then most of the time I will collapse into the ground state. And the phase will give me the phase corresponding to the ground state energy. But now, of course, we know we cannot measure the phase. It can't be observed. We can only measure relative phases. And so what we do is we compare the state psi where we evolve it with the state psi where we don't evolve it. And I want to know the relative phase between the two. And the way we do that is with a controlled evolution. So I take an ancilla here that I initialize in the state 0, and then apply a Hubbard gate to it to put it into the state 0 plus 1. And then controlled by this, here I have my wave function psi. Controlled by this, I apply the unitary u, which is just exponential of minus I h t. So I applied only when this control qubit is 1, and I don't apply it when it's set to 0. So what do I get here then? What I get here is basically I start here, that here so I started with 0 and psi. Then here I get the state 0 plus 1 over root 2 times psi. And now, so that's what I had here. And now when this control bit is 1, I evolve. When it's 0, I don't evolve. So then here after that, The state that I have here is 1 over root 2 of 0 and psi and plus 1. And here I have evolved that. So here I get an exponential of minus I e t times 1 and psi. And if I move the psi again out of the bracket, then have 0 plus exponential of minus I e t times 1 times psi. So if I now measure that qubit, I can extract from that the phase. What we do in practice then is we apply here another h, for example, to it, and then we measure, and then if the phase was multiple of 2 pi, we measure 0. So when it's the odd multiple of pi, we measure 1, and when it's here in between, we measure something. So we just measure the phase, and there are many ways of doing it smarter, but that's the basic idea. I get the phase under the evolution. So I may have to run it many times here, and then I get one phase locked in. So what I need for that is I need to evolve under the Hamiltonian H. So what I do is I prepare some good guess for the ground state. Starting maybe from some mean field state, I could just take the mean field state, or I diabatically evolve it. Then I use the quantum phase estimation to project an eigenstate. And then the eigenstate with the lowest energy that I get is what I assume to be the ground state. Now here people ask how likely is that to succeed, because we know that finding the ground state of quantum models is QMA hard. In general, we just cannot find the ground state. However, what I say is, if it's so hard to find the ground state, then nature will also not find it, and I cannot find it in the lab. Then I cannot take the molecule, and if I cannot get it into the ground state by cooling it down or doing something simple to it, then I don't care that I cannot simulate it. I only care about calculating the ground states of materials or molecules that actually can reach the ground state in a short time. It's the same as protein folding. We know protein folding is an NP hard problem, but what you also know is if a protein takes exponentially long to fold in your body and it will misfold all the time, it only causes problems. So the proteins that work in nature are those that fold quickly into a specific unique state. If they don't, it causes diseases. So those proteins we care about, we can fold easily. Those we can't fold easily, we don't care about because they don't work in nature. Same here. If there's no way I can prepare the ground state in the lab, and then I don't care about not finding it because it's useless. And if I know how to make it in the lab, I can mimic that. So all we need is we need to time evolve with the Hamiltonian for the diabatic state preparation. We need to time evolve under the Hamiltonian with the quantum phase estimation. There's a third method one can do. The third is you can make a variational ansatz, the variational approach. We just run some circuit to prepare a state that is parameterized by some angles. So you make a state made from U1 of theta 1, U2 of theta 2, U3 of theta 3, and so on, to some unitary UL of theta L, applied to some state, for example, all zeros. And now you simply make that, you make a state, you measure the energy, and you tune the angle theta to get as low an energy as possible. The advantage of this is these can be quite short circuits that you can do on the noisy machine. But this is hard to scale because we don't know how good the wave function is. So now I want to talk about doing that for chemistry. In chemistry, we have a model like the Hubbard model, but the problem is the Coulomb interaction is long range. And so the model we get in the end is one that is long range and has more terms. Who of you here has a chemistry background? One person, good. So how do I actually make a model for a material? Who knows how to model or to simulate a material classic? Has anybody calculated the yeah? Yes, so you put some atoms on lattice positions, and then you do DFT, which is a mean field type approach. But the wave function lives in this infinite Hilbert space, right? So what we do is we place the atom, and then we introduce a basis set. A finite basis set, hopefully, if you want to calculate anything on a finite computer. What do we choose for these basis sets typically? Orbitals. Yes, so you do something that mimics atomic orbitals. Some Gaussian function, something centered around the atoms. Now, okay, that's great. They can take some the orbital around this atom and some around that, but those two will not be orthogonal. So typically, the basis that they choose to mimic the atomic orbitals to have a good basis. That's a great choice. But if I have one around this atom and one around that atom, that will not be orthogonal. What do we do? One thing is to orthogonalize it and then always pull around this complicated basis states that you do. So you can actually do quantum mechanics in non-orthogonal basis sets. And what it turns out to be, in the end, you want to solve H psi equal E psi, the Schrödinger equation. This is a bit changed. What you get to is H psi equal E times the overlap matrix S of your eigenstates times psi. And all works out beautifully. In the end, you get to an eigenvalue problem that is just the generalized one instead of a simple one. Works out nicely. Except if we want to now map it to a quantum computer. The eigenstates of our qubits are orthogonal. So you cannot just map the basis states I choose here to qubits directly, because for the qubits I need an orthogonal basis set. And then I ideally want something where I have a good guess already for the ground space. So I have to orthogonalize it in some way. And what we typically do is then we use either the DFT or Hartree-Fock method to get an approximate eigenstate and an orthogonal basis. So you use density functional theory or Hartree-Fock to get an approximate solution. That basically gives me a product state in a certain orthogonal basis. Then I choose the one-body basis that I get from that, and I have an orthogonal basis. and an approximate eigenstate. Approximate ground state. If I want to improve it, I go back to an adiabatic state preparation from this ground state. And now I need to write down the full Coulomb problem in that basis. And that has a pretty simple form. And the form is H equals a one-body term, this is sum over P and Q, some constant HPQ times A P dagger AQ when the AP and AQ are the fermion negation and annihilation operators, and P includes the orbital and the spin index. Plus, I have the two-body term, which is the general two-body interaction, sum of PQRS and HPQRS, AP dagger, AQ dagger, AR, AS. This is the general form of a two-body Hamiltonian in the second quantized form. Now, all I have to do is I have to evolve with these terms. And we've looked at the terms already. This was just the hopping term we had in our the Fermi models. That model and that term can in the same way be mapped to a nice and easy quantum circuit. So for each of the terms, they can write down the circuit to time evolve for a short time. And each of these terms takes at most of the order n gates because they have to do all these C0 strings that we had to count the fermion parity. So what is the, we stop here because the Coulomb interaction is a two-body interaction. So that's a great question. Coulomb is just two bodies. So I want to calculate the matrix element between two particles. So that's why it's only fourth order. When you go to nuclear physics, we had that on the list. If you want to go to an effective model in nuclear physics, then we go to three-body terms and four-body terms. If you want to simplify your basis by saying you take few orbitals and just take an effective model, then you may get three-body terms. But if you do just the bare full Coulomb model, it's a two-body interaction, so we stop at 4. And I'm not unhappy for that. So now let us look at the complexity of this. One time step it has how many operations? I have big O of for n orbitals, of for n spin orbitals, I have n to the 4 terms. So I have n to the 4 terms. The circuit depth for each is O of n. That leads me to big O of n to the 5 complexity for one time step. Now the question is, how small do I have to choose the time step? And that depends on which version of the hot decomposition you use. In the simple the first order one, the time step has to go with 1 over the square of the number of terms. In the second order one, the time step, the t that I choose, has to go with 1 over the number of terms to the power of 3 over 2, where m is the number of terms, and m is n to the 4. That means for the propagation over some time, t, I need to do n to the 6 time steps. And then the scaling overall is big O of n to the 11. And information theory calls the deficient because it's polynomial. Any computational scientist who actually writes code runs away screaming even from an n-cubed algorithm. With an n to the 11 algorithm, I actually prefer 2 to the n to n to the 11 for all values of n that I can ever calculate. Because yes, asymptotically n to the 11 is better than 2 to the n, but I have to go to a pretty large number of n for that to happen. So when you plug that in naively and count the number of gates you have to do, and we choose an n of a size that something is just barely beyond what we can do classically. In a classical computer can solve something with n equal 60 or 70 can still be done exactly. And so let me choose n equal 100. When you choose n equal 100 and you have n to the 11 steps, then we are at about 10 to the 22 for the circuit depth, naively. So we are at the runtime of the age of the universe. So although it's efficient, and although we know we have an efficient algorithm for doing that, it's not as nice. Asymptotically it will be better, yes. The Kuhlmann is density in real space. So what we could do instead of going to that basis, we could just go to the real space and just make a real space mesh. So now we make a real space mesh and calculate it in a real space basis. In a real space basis, it becomes n squared. But now how many? Okay, so it's n squared. So now the scaling becomes better. I have only n squared terms, so now it becomes n squared to the power of 5 halves. So now it's an n to the 6 algorithm. Excellent point. But now how many mesh points do you need to describe a single atom? I need maybe just 10 orbitals to describe it, in the case of the hydrogen 2. But with a real space mesh, I may need 1,000 mesh points, because I need at least 10 times 10 times 10, and it's still pretty coarse. I probably need 100 cube. So probably need about 1 million mesh points per atom. But then I can describe it. So then this is the basis size here. Now I have 1 million basis functions. So I need more qubits, and now the scaling is better. N to the 6, but n is the factor of 100,000 larger. So yes, asymptotically I will win. The crossover we estimate to be unlikely. You can also, and I'm surprised that that didn't come up yet, because actually you should simulate quantum electrodynamics. Then it's purely local interaction. Let's simulate the gauge field. Let's simulate the photons and the electrons, then it's purely local. But you probably need a much finer mesh and a much shorter time step. Then it's linear in the size. So these are all things that need to be explored. My rough estimate is with a real space mesh, you need more, so that for practical sizes it looks worse than even that. But that's something one has to work out. We've worked it out exactly for the second quantized form. We're working it out for a plane wave basis set now. Because with plane waves you can also do it in n squared. Because you live in K space first, then you make a Fourier transform to real space, but you have a nice plane wave basis set. You typically need about 100 times more plane waves though than localized less orbitals. if you ignore the inner shells of the atom. If you want to include the 1s, then you need billion times more. So we need to work that out. So yes, one thing for sure is n to the 11 is something to run away from and to start thinking about what else can I do. Real space, k-space, plane waves, QED. How does it work? The scaling becomes better. If I do it with quantum electrodynamics, I'm down to a local model, and the scaling becomes much, much nicer and easier. It becomes linear problem. But then you need this fine mesh and work it out. You probably need then about 1,000 mesh points per atom. So you need about 1 billion qubits to start with. So let's assume we have a small machine like with 10,000 qubits. I want to start with a small basis set. Once you give me something with 1 billion qubits, yes, then I will do QED likely and check if that works out. So we can start thinking about that now. And I want to walk you through what we did for this case that looked so bad. It looks bad, and naively you think it's about 10 to the 22 operations. I want to bring it down to about 10 to the 14, 10 to the 15, so I need to shave off about the factor 10 to the 8 in cost. And that's something that I don't shy away from because we've done that quite often in the past for classical algorithms. So we then worked on that for about 2 years to bring the cost down. And there are many ways one can bring the cost down. So that in the end, I can tell you the answer now. We brought it down from n to the 11 to about big O of n to the 5.5 roughly, empirically. How did we get there? One step was these bounds are wrong. These Trotter bounds are based on proofs for the upper bound of the error. And if you have m terms, you do about m triangle inequalities, so you get an extremely loose upper bound. And in practice, this is what we observe in small molecules, where we can measure things. The scaling is much better, and we don't have to change it with n to the 6, but it's sufficient to grow it with about n to the 1.5 for molecules. And the constant in front is also about the factor of 10,000 smaller than the bound. So these are extremely loose bounds. So we're fortunate the actual scaling is much better. That brings us down by a big factor already. Then there are, so that was one thing we did. The first is the empirical Trotter error. Error is much better than the bounds. If somebody could prove better bounds, that would be great. We have better bounds that bring it down, but they're still pretty loose. The second thing we did was we did adaptive time steps. We have n to the 4 terms. A few of these terms are large, but most of the n to the 4 terms are tiny. This is so. The way you see that is that the integrals here, these terms here, they come from taking the integral over the basis functions at 4 locations. I have one sitting here at P, at Q, at R and S. Now I'm doing the integral over space, over the basis function at P, the basis function at Q, the basis function at R, and the basis function at in the orbital S, that integrated over space. If PQ R and S sit on the same atom is pretty large. When they are far apart, the overlaps are tiny, the integrals are tiny. So most of these terms are tiny. I cannot ignore them, but they're small. So what we can do now is those terms that have a small amplitude, we don't propagate them every time step. We might do them only every 100th time step, but then with 100 times larger time steps. So do the small terms less often with large time step. Once we start doing that, there's no more proofs of bounds on the error. So nice all empirical. But this makes it at least a factor 10 faster on the small molecules. It might even give us a big scaling advantage. Let us assume it just gives us the factor 10 or so at least. Yeah. The small terms I don't do them every time step. I skip them most of the time. And after 10 time step I do them, but now with a 10 times larger time step. So I do the small terms with a larger time step. If I keep the time step small, then I'm doing every term at every small time step. And then every time step I'm doing n to the 4 terms. But now what I can do is when I have a tiny term, then I might say I do that only every 10th time step, but then I do that with the bigger time step, and then it comes in only every 10th time step or so. Less often with a bigger time step. That has been used widely when you simulate the solar system. When you simulate here the sun, and here the Earth, and here the moon around the Earth. You need to take a small time step for the moon around the Earth, but you can do the bigger time step for the moon. So this is quite common. You do the big forces with small time steps, and the weak forces with larger time steps less often. That can help a lot. We can't prove anything. We can show that on small ones it helps at least the factor 10. We assume a factor 10 for now. Likely it's much bigger. Then the third is we optimize the Jordan-Wigner strings. Remember when we had the fermion terms, we had to calculate this product of sigma c's. And we did that by doing lots of C naughts, because I had to calculate the parity. And then I undid that again. And that takes order n steps. Now, you could think, let's use something else than Jordan-Wigner. There's, for example, the Kita-F3 method that does it in log n steps, but it's much more complicated. So what I do here now instead is something much simpler. Let's say I calculate the hopping term from here to here. For that I calculate all this parity. And then I uncompute it or not, because in the next time step, what I could do is in the next time step I calculate the hopping from here to there. And so if I have already calculated the parity of these orbitals, then I don't have to uncompute it. I can just store that in an ancilla, and then when I go to the next one, and now I need to calculate the parity to here, I just need to add one extra orbital to it. So when I sort the terms in the right way, then I can reuse most of these calculations, most of these long C0 strings. So maybe I have the string here, then I do a rotation, and then I do the Jordan-Wigner string back. So I do all of these C0s again back. And then I take the next term, and now I redo all of these C naughts. And if I sort them in the right way, then these just cancel. Then when I start and I redo it, then I can just cancel out. So when I sort them in the right way, the cost of the Jordan-Wigner strings goes away. So I'm losing the factor n here. It is amortized constant. Yes, it costs order n in total, but when I do all of them, in total it only costs n to the 4. So this comes down to n to the 4. No, you see, these are all only nearest neighbor C naughts because I need this 1D ordering for the normal or the ring of the fermions. Because I have them sorted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, and I just need to do the C naughts between adjacent ones. It's just a 1D layout that I need. If I have long range, or longer range ones, then I can do more. I mean, now, or when I do things smartly, I can now start doing things in parallel. And when we had the spin model, remember, we could do all of the X rotations in parallel because they all act on different qubits. For the hopping here, it's hard because if this one here hops from here to there, this Jordan-Wigner string touches all of the qubits. So naively, it seems that we cannot do two terms in parallel because this term, for example, and that one here, they touch the same qubits. But then, what one can realize is if we again sort the terms in a smart way, then I can do this term that is sketched here and that term in parallel. Because if you hop an electron from here to here, it will not change the parity of the electrons between here and there. So when I nest these terms nicely, then I can do up to n terms of them in parallel. So bring it down even more to big O of n cubed by circuit depth by nesting. So now we save the factor n squared, we gain something here that looks better, and we have more tricks. For example, we had the quantum phase estimation. Where did we sketch that? Did I erase that? Or is it still here? Is it somewhere? Or is it gone? It's under this one? Yes, thank you. So we can save a factor 4 here. This is how you typically learn quantum phase estimation. You operate when you apply the operator when the ancilla is 1. You don't apply it when it's 0. In the end, what does the control U do? I do all of these big Wigner strings here, the C naught, here, that I undo. But the only thing that I have to actually control is the rotation. Because the rest is just a unitary that I then uncompute. So the main cost here is then the rotations that I have to do. And so let's think about how do I do a controlled rotation. So assuming I have a rotation gate, how do I do a controlled rotation? I have an ancilla. I want to do a rotation here by an angle r of theta, by an angle theta, that's only if the ancilla here is set to 1. We typically don't have controlled rotations in our hardware. We have a C naught, and we have single qubit rotations. So what I then do is I can, now let me get that right, is I can do a rotation by half the angle, theta over 2. Then I do a controlled knot. Then I do a rotation by minus half the angle. Then again do a controlled knot. What happens here? If the ancilla is 0, then nothing changes here. I rotate back, and I do nothing. If the ancilla is 1, then I rotate. I flip my qubit, and I rotate by the minus the angle, which is again rotating by theta over 2 in the original basis, and then I flip it back. So every rotation, every control rotation turns into 2 rotations. Now, what is the change I'm going to do in the phase estimation? Normally it is I do the controlled rotation. I don't do that because basically what I do is I do a controlled rotation if this is, so I do a control rotation, so I do a control of U. I also do an anti-controlled with U dagger. I do that at the same time. So what it means is basically if the ancilla is 1, I move forward in time. If it's 0, I move backward in time. So instead of 1 being constant and 1 going forward, I now go forward and backward. So the first thing is I get twice the time. So what I want to do is I have this here, and now I want to go to 0 times exponential of plus IET times 0 plus exponential of minus IET times 1. But what that also means is that all those rotations that were controlled rotations now are not controlled rotation, now they're simple rotation gates. So what this here means is that all of these controlled rotations, when I do this, turn into single rotation gates. So I don't do a controlled rotation in here. But what I do is I just do a rotation by an angle theta. So we save a factor 2 in time because we go twice the phase. We save a factor 2 because we do only a single rotation instead of 2. That saves us a factor 4. I'm really happy also for factors of 4. 4 here, 4 there, they multiply up. So in the end, when we then looked at that, the circuit depth came down for that problem size of n about 100. We shaved off about 10 to the 7 in circuit depth. And the scaling is not as bad. The scaling might still look bad, but remember we have n to the 4 terms, so the minimum scaling is n to the 4, even classically. There's a big problem classically even. So we are only slightly worse than that. And we could shave off a factor of 10 to the 7. And with that now, the naive estimates said that this is totally doable. So there are, okay, yeah, and so before going further, it's okay, yeah. With that, I need about 10 to the 12 gate operations. In circuit depth, that's all doable. So with that, we said now it's actually realistic to do chemistry. With that scaling and 10 to the 22 gate operations estimated, it was impossible. Now, there are lots of papers recently in the last year on new methods for Hamiltonian simulation based on linear combination of unitaries, on truncated Taylor series, and more. There are lots of them. They all have far better error bounds than the Trotter scaling. They look much better, but in the end, when we plug in numbers and when we look at it empirically, for molecules, for all of these methods, the scaling is about n to the 5.5. The bounds that are proven are actually tight. For in Trotter, they're loose. So they look much better than the simple Trotter method. So far, empirically, for almost all models, the Trotter method has been shown to be the best. It's the simplest method, and it's so far still the best. We don't understand it yet, and we still look for a better method. What one has to do thus is not only look at the asymptotic scaling of upper bounds for the runtime, we need the actual runtimes, which when the bounds are not tight, you really have to implement the algorithm and run it and see what the error is. And then you need to also know the constants. As we mentioned, the localized the space sets in real space, the scaling of terms is n squared, but I likely need a factor of 10,000 to 100,000 more basis functions. We need to find out how many exactly more do I need for the same error. And then in the space method, have to calculate 1 over the distance between the two sites. Either tabulate that somewhere and then have to look that up in a huge table, which is slow, or calculate it with arithmetic, which needs about 1 million gate operations. So the constants will be huge. So we really have to implement the code and work it out and run it through and count the number of gates I need and then compare. Because while the asymptotic scaling can give me ideas which algorithm is better, in the end I do not care ever about the limit of n going to infinity. I always only care about finite n. So while an n squared algorithm is almost likely better than an n to the 11 algorithm, I don't know whether an n to the 8 algorithm is better than an n to the 11 unless I work out the constants and what n is. So I really encourage all who work on quantum algorithms to also give us the constants. Because to make it practical, that's super important. And just to claim that something now goes with n to the power of 3.5 when the n is not the same n is misleading. Like you could say when you go to a plane wave method, we may bring it down to n to the power of 3.5. That assumes that it's the same number of n, but you cannot use the same number of plane waves, or the same number of the local space state as you use for the optimized orbitals in space. You need many, many more points in space or plane waves than orbitals. So you need much bigger n. So you cannot compare apples and oranges. That the apples to the power of 5.5 is not necessarily worse than oranges to the power of 3.5. We really need to work it out on specific molecules and materials. And let me now look for a slide that I wanted to show. We looked at the end at, okay, so this is the summary of what we got for a simple the test molecule, where the first code looked like if I had a gate time of 10 nanoseconds. So in the meantime, I would not use that. I would use a value that is at least a microsecond. So let's say I use the microsecond gate time for logical gate operations. I would need about 3,000 years. After what we improved, it got down to 3 hours. 3 hours seems reasonable. 3,000 years seemed, well, I can't do that ever. But factors of 10 to the 7, as I mentioned, one can gain. And I think one can gain much more. But especially I think that the trick, no, that's where I need global search now to find the right board. So the trick of adapting the time steps, I think we can get much more here. I think we can get another factor of 1,000 out here. But then, next we want to say, let us now apply that to a real problem and take the next step of actually adding the cost of quantum error correction. And we looked for something that people would like to solve, and that was the problem of biological the nitrogen fixation. Most of the fertilizer is based on ammonia, and ammonia you make from nitrogen with hydrogen. Just by saying you take nitrogen, you break up the triple bond, you attach 3 hydrogens to it, and you have ammonia. And for that you have to break up this strong triple bond. We have plenty of nitrogen in the air, we have less hydrogen, but one can do that, and that's the Bosch process that's still used after 110 years, that uses high pressures, high temperatures, and about 3% of the world's natural gas production just to feed the hydrogen into it, and it turns air into ammonia for fertilizer. But you also know that in the root system of some plants, there are microbes that can turn nitrogen from the air into ammonia at ambient pressure at room temperature without any natural gas. People knew that a long time, and that's why there are usually and that's when times before fertilizer, one did crop cycles. Every third year you planted beans, and the fourth year nothing, and the beans had in the roots the microbes that made fertilizer. So we know there is this molecule that can do it, but nobody understands how it can do it. And I can show you why it's so difficult. This is the enzyme that does it. If you zoom in, then in the center, there is this complex, Fimoco, which is the iron molybdenum complex. There's one mystery atom here, surrounded by 7 ions and one molybdenum atom. So you have 8 atoms with d orbitals. This is totally correlated, and we cannot classically calculate the energy of that accurately enough. Now we want to see how, when this comes together with nitrogen, how it splits apart the triple bond and so on, how it does that. In order to follow the reaction, we have to actually know the energies accurately of all possible states of that, and then find the path for the reaction. And we cannot classically calculate the energy of that molecule accurately enough. We have an error that's at least 10 times room temperature, so it's useless. We don't know which path the reaction takes. This mystery atom here was identified only about 10 years ago. It's a carbon atom. So till 10 years ago, we didn't even know what it looked like. Now at least we know that, and we'd like to calculate the energy. Now this is thousands of atoms. So we have tens of thousands of orbitals, and the scaling of 10,000 to the power 5.5, well, you can forget that. So what one does is one does a classical calculation for the big molecule. One extracts an effective model for just the correlated part. So you start with a big classical calculation. You generate the structure, you optimize it to find the local minimum. You then find the orbitals that describe the active space that is correlated. Then you calculate all of the integrals here, these terms here, and then you want to solve that problem exactly. For smaller active space, you do that with something called full configuration interaction, which means you basically just exactly solve this problem. But that's limited to about 50 spin orbitals. This here has at least 100 to 200, so it's far too big. We cannot do it classically. So that's where we plug in the quantum computer to calculate the energy. Then we feed that back into the big calculation, doing the classical reaction mechanism. And then we look at how do we actually implement that on a quantum computer. And we talked about the algorithm, and we know the scaling. But now it's a bit more complicated. Namely, I have to do rotation gates. All the time I have to do rotations. Who knows how rotations are done in a fault-tolerant way in a quantum computer? If you have an arbitrary rotation, then you cannot error correct it. Because there's no way I can tell that if I make a rotation by 1.01, whether I wanted to make one by 1.01 or whether I actually wanted to do it by 1.02. So the only way we can actually make it get error to correct it is that we have to build all rotations from discrete rotations. That's where the T gates come in. I want to build them all by rotations by pi over 8. And so but I want to do angles that are more than just pi over 4. So what I do is I have to do a sequence of Hadamard T gates, a long one, that then approximates the rotation I do. So I can synthesize a rotation by about 200 other gates. That means now my circuit depth suddenly exploded by a factor of 200. And then I have to prepare those T states, which are the T gate applied to the zero state. And making those is hard because I cannot make this rotation to a precise angle in hardware. So what one does is one runs negative factory, which basically is you take many approximate rotations, then you run that to an error correcting circuit essentially to prepare one good rotation. So that means that for each rotation I have to do here, I have to do about 100 Hadamard gates and about 100 T gates, and each T gate needs about 100 other gates to produce it. That means basically every rotation gate we had in the circuit is not one gate, it's actually tens of thousands of gates that I have to apply. So if I do that sequentially, then suddenly our runtime go a factor of 10,000 larger. And you go from 3 hours to 30,000 hours, and now I'm beyond the time of a PhD student. So thus what we do is we want to parallelize it. We want to do them in offline line factories and make lots of your T factories that make the T states. Use those T states to make certain angles in parallel rotations so that then in one time step I can insert the rotation always. That brings down the cost of rotations by going parallel. So we looked at that and the cost of that. And then we looked at the Trotter error, and here I want to show you, we estimated what it is. And for a set of small molecules, we calculated the Trotter error bounds. These are not the naive bounds. These are much, much tighter bounds already up there. And we measured what the actual Trotter error that we measure is for a small molecule. And we find that the actual error is about a factor of 10,000 or more smaller. So now what we do is we could not take this and we could extrapolate it. So it's basically nearly constant. We don't do this, but what we do is we say we have the scaling of the upper bound that we have, and let's just assume the scaling is the same, but just the constant is reduced. We just pull that down, and then we get these curves here. So then we estimate for the problem we need, which is this size, we need about 100 trotter steps per time unit. Empirically, I think it will likely be even much smaller. And then we work out what is the runtime if I could do a logical gate at 10 nanoseconds. That's kind of still the science fiction machine. I would rather increase it by a factor of 1,000 in the meantime. If we could do that, then if I do a nice way that is parallel, I need about a day. If I do it sequentially, I need about weeks to a month for two different problem sizes. But I need only between 100 or 2,000 logical qubits. And next, we estimated the cost, including error correction. And here we assume 3 different qubit qualities: 3/9, 6/9, and 9/9 fidelities. Let's look at 3/9, which is what one might be able to achieve with transmon qubits, if one is lucky. So this is basically what one aims for with superconducting qubits. Then we estimated if I want to have 109 logical qubits, how many physical qubits do you need per logical qubit, and how many physical qubits do you need to just store the wave function. With 3/9 fidelity, it's about 2 million. With 6/9, it's about 100,000. 9/9, about 34,000. But 2 million qubits is a lot, but not impossible. Next, I want to do the rotation factors. I need 26 in parallel. For each one, I need, depending on the qubit quality, between 300 and 17,000 qubits. So I need a total of about 8,000 to about 500,000 physical qubits for the rotation. Okay, that's fine. That's cheap. Next, I need the T factors to make the T states. With 9/9 fidelity, I need about 5 million to do the T states. With 6/9, I need about 30 million. With 3/9, with maybe what I could achieve with superconducting qubits, I need about 5 billion physical qubits. So seeing that, we say, yes, it's feasible, we can do it. Because we have built systems with more than billions of transistors, so we should at some point in the future also be able to build something with 5 billion qubits. But I'm really scared of having to build a device with 5 billion physical qubits. If these are transmons and each one is about a millimeter in size, then this is a football field size machine. So what I learned from that is, yes, in principle, it's possible, it's feasible. I don't have to go to the science fiction. This is doable. But I don't like having to build that. So I want to get the qubit to be better. So one thing is we need better qubits, and that's why Microsoft works on top for the logical qubits that promise to be much better. Because we know with these qubits, the engineering will take decades. So we must better build the better building blocks first. The other thing is we need better algorithms. We need more advances here. We need to explore what if we go to real space, to plane waves, and so on. What is better? What are the constants, and so on? What is the best algorithm? But really work out the constants. Then we need better error correcting code. If, as here, 99.9% of the qubits are used just for the T factors, we know where to start optimizing it. And so Chong Won von Haar and Matt Hastings, they looked at it and brought this cost down by about the factor of 100 already. So we need to have better T factories, we need to have have deeper error correcting code, and we need to have better algorithms to make it really feasible in the short term. Because 5 billion, I don't think we'll get that in the next decade. Now, but if we go to simplified models, for example, like a Hubbard model, then it looks much better. But it does not look better at first. For example, let us look at the room temperature superconductor. What we actually have is about 50 bands per unit cell. We want to study at least a system size 20 times 20. It gives us an N of 80,000 with a scaling of N to the 5.5. If I just do a naive model of that superconductor that was mentioned, then the runtime is the age of the universe, even with the best algorithm you could think of. So what we do for the superconductors is we simplify it. We go from the full model, we look at the 3D structure. In the case of the cuprates, one finds there are some 2D copper oxide planes. We look at the plane and simplifies it just a single orbital per atom. And then one has a simplified model, the Hubbard model. And with that, it looks much better. Because for the Hubbard model, the number of terms is linear. The scaling looks nice. And I take a system of size 20 times 20 for the Hubbard model. I have about 800 terms. I can apply them all in parallel. The circuit depth scaling is about constant. And the runtime to solve it, if I had a gate time of 10 nanoseconds, is about a second. If it's lower, like if it's milliseconds, it's still not more than 1 hour. So that is totally doable. And what one now has to do is one has to kind of find somewhere to go from the Hubbard model to the full material. Kind of do some compromise. Take the Coulomb, but not all. Learn the phases, the physics. And stand and then measure things in the lab, build things. So we can do lots with effective models. It's hard to do things brute force. So when people say with a quantum computer, condensed matter physics is boring because then it can all be solved by the computer, I disagree. Because naively, yes, it can be done in principle. It takes the age of the universe. To do that, you still have to be smart and find the right physics models. And instead of being the end of quantum metaphysics, I think it's the start. Because then we have a great new tool for solving models. And that will be a great time. And the reason why I joined Microsoft, I can admit that now, is my master's thesis project decades ago was I should do a quantum Monte Carlo simulation of the two-dimensional TJ model to understand the mechanism of superconductivity in that. And I failed, because on the first day we realized there's a sign problem. So we couldn't do that, but it still bugs me that I failed at my first attempt there. So I want to solve at least the Hubbard model. To do that, I need to build a quantum computer, and that's why I'm now at Microsoft. And that's the goal that I have. Thank you. So the summary is, when you try to apply new algorithms to problem, you find out you need to know about the constants, you need to know about the problem, you need to know about how to use solve stochastically. So those are the next step that we urgently need now to find more application of quantum computers. So we need to have a new class of people who do applied quantum computing research, quantum software engineers, who write code to optimize it, make it fast, and then say, yes, once somebody gives me a quantum computer, I will solve global warming. But you can write the program already now. Questions? Yep. Yep. Yeah. You can just efficiently simulate nature doing it. The scaling is only n to the 11. If you know what nature does, like if you know what you do in the lab, then you can basically plug that into H and simulate it, in principle. Yeah. Nature. So because we think we understand the Hamiltonian that describes chemistry. That there's no hidden order there. We think that quantum mechanics plus Coulomb interaction is the right model. Nature has no secret oracle beyond that. Well, if nature has it, then I want to find out about it. That would be more exciting. Yeah. Yes. Yeah. Yes. So the Clifford gates are protected. So relatively the T gates are not. So we still need good T factor. No, we just do some unprotected T gate with the error rate of, let's say, -10 to the -3. Then we apply distillation circuit on that, with which gate volume of roughly 80 per T gate gives us a T state that is quintically better. That has 10 to the -15 errors only, and some qubits that I throw away. So from 8 noisy T state, I make more one that is much, much better in software, basically. That still means that most of the machine is T-gate. Yeah. So that's what we want to bring down further. Yeah. For this case here, it was 5 smart people thinking about it for a couple of years. And so if you think, but then we had to learn. So it might be that it's now in hindsight it's totally trivial, but that's always the case. So algorithmic developments, let's say classically, where we know more, for example, just for a classical simulation of the Ising model that we talked about, there is statistics over 25 years from about 1980 to about 2004. And in that time, the advance in algorithms in 3 big jumps outperformed the advance due to Moore's law in faster hardware. So running the algorithm from 2004 on a machine from 1980 is more efficient than running the algorithm from 1980 on a machine from 2004. Well, you know there's typically such a breakthrough in methods happens per field every 5 to 10 years. And then it gains the factor of 10,000 or more. So this is hard. Because you need to explore ideas that you think could work, and most ideas that you try in the end don't work. But in the end also, the ideas that work are simple in hindsight. It's nothing deep. It's simple like do the small terms with a larger time step. So it's a very simple trick, but most simple ideas just fail. And finding the good ones is hard and the art. And because the typical time scale in the classical world of making breakthroughs is about a decade, that's why I say it's time now to start thinking about that for quantum if we think we'll have a machine in 10 years. Yeah. Yes. Yes, I can make a comment on that. That is, you have some state that you have to prepare like this, and then you want to choose those angles in the optimal way to get a state that has as low energy as possible. Because there's still just an upper bound for the ground state energy, and the wave function you get is an approximation. But leaving that aside, okay, and you have to find these angles, the right ones, that give you that state. Let us look at what does it cost to, once you have that wave function, to get the energy. The way they do that is they individually measure the expectation value of each of these terms. So they have to measure the expectation value of all of the n to the 4 terms. And each one has to be measured very accurately. So now you can roughly estimate how many measurements that takes. That's then the upper bound. And I think we should do it more precisely. But let's say we have to measure n to the 4 terms. And each of these terms have to measure accurately enough. What does it mean? I want to measure it. I want to measure the total energy, typically to at least the accuracy of room temperature. That's about half a millihartry. The typical scale of the terms, the constants in front here, are tens of hartry. So typically have to measure each of the terms to 5, 6 digits of accuracy. That means I'm doing n to the 4 times typically about, let's take a lower bound of 10 to the 10 measurements to get these 5 digits. But then the error sum up of these n to the 4 terms. So if I want to have the total energy to be 1 millihartry, and I have n to the 4 terms, and each one of them should have at least 1 over n squared smaller error. So I actually have to multiply it with another n squared. I have to do about n to the 6 times 10 to the 10 measurements to accurately evaluate the energy at scale. Which will then, if I plug in n of about 100, then that's about 10 to the 22 measurements. It's probably an upper bound. Probably it's only like 10 to the 12 or so. But this is for each step in the optimization. You have to run that algorithm and prepare 10 to the some huge number of states. Why does it work for hydrogen? N is 2. The scale is not so large. It's basically 1. You want it to about 1/10 of the coupling. So you do, so when you plug in n of 2, and this is just 10 to the 2, then it's doable. But as you scale up, the scaling is just bad. So these methods work well for noisy small systems, but it doesn't scale. Now what one should actually do is taking these values from real molecules and work out what that number actually is. But even if it's just 1, it's still 10 to the 12. So these methods are sold as being scalable. When you talk to the authors in private, they acknowledge that. Yeah. 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 Good point. So this is basically digital versus analog. We had that also in the classical world. The first the first classical computing machines were analog. And the problem why we changed from analog to digital is when you did machine for adding numbers, you can store them in charges, in voltages, but you cannot measure them to better than about 10 to the minus 4. Once you want to sum up millions of dollars, then it's not good enough anymore. Then one went digital, which was far slower and more complex, but it's scalable. And right now, who still has analog computers at home? Now, until the 90s, one had analog computers to integrate linear differential equations through LC circuits, and it was just super fast. Yeah, you ran it, it made sound, you heard the resonance, it's super fast. In the meantime, the digital machines are faster. But what is happening now as one goes towards machine learning, and we don't care about the exact numbers, but just that it's fast and cheap. People think about things like the neuromorphic chips, which bring some of the analog world back there. Quantumly, it's the same. It is much easier to build the Hubbard model with atoms in the lab rather than build the logical qubit and simulate it. It has the same problems like D-Wave. Temperature. It's extremely hard to cool it. But for the Hubbard model, basically the lowest temperature achieved in optical lattices is a few thousand Kelvin relative to the Coop rates, which is great because at those temperatures, the Coop rate materials melt and they cannot explore the properties of the high temperature, the Hubbard model. That's interesting. So because they cannot cool it well, it's more something for the high temperature phases. It will be very hard to get the ground states. And then there's calibration errors. How well do you actually know the P and U? And that's now exponentially sensitive to the lattice height. It's hard to calibrate that to more than 10%. So yes, it's much faster, cheaper, easier, but because it's analog, it has all the limitations of an log computer, and those you don't get around. So in the short term, at first, that, in the long term, digital, I think that will be just like it was in the classical world. And then at some point later, we may build some hybrid, special Hubbard model qubits, whatever, for that. Is a human brain a classical computer or a quantum computer? That's a very interesting question that many people think about. It goes back to Pauli and Jung, sort of how much of what one sees in quantum mechanics appears actually in psychology. The something chronicity was termed then, because whenever Pauli went to Jung's house, some vase fell down or something happens bad. So people still debate whether the brain is quantum or classical. What may be more interesting is the question of could the brain maybe described more easily quantum mechanically rather than classically, because just like in quantum mechanics where the order of measurement matters, with the human mind, the order in which I ask question matters. So maybe the same math structures could be used to describe the brain without the brain being quantum. But this is a deep question that many people have thought about for decades. Yeah. Yeah. Let's say if you give me the Hamiltonian of that spin glass with the nuclei and everything, and around the heat bath and all, then I can simulate efficiently with the most polynomial overhead. So yes, if you think that you know the Hamiltonian describing the system, then I can simulate it efficiently on a quantum computer. Efficient may still mean the scaling is horrible, but at least in principle, so at least on a smaller version I can do. I cannot find the ground state of a spin glass on a quantum computer, but neither can nature find the ground state of a spin glass. Yes. Yes, but if the model faithfully describes nature, then I should be able to predict what nature will get after a while. And finding the ground state of a spin glass is NP hard. It's unlikely that I can do that on a quantum computer. In experiments, we see the energy drops on an exponentially long scale. Yeah. So spin glasses are spin glasses because they do not equilibrate. We can't do it. They are super strange, and they don't reach the ground state. If they did, then why can't I just simulate a spin glass with super conducting qubits like D-Wave did, and solve all NP complete problems very fast? Now D-Wave says that they can solve NP complete problems, and I agree. So can my laptop. Just takes exponentially long. Logical or physical? 10,000 physical qubits, I would take an optical lattice with 10,000 atoms and say, here, there are qubits. Or, yeah. Logical, 10,000 logical qubits, if I think of error rates of 10 to the minus 3, and what they would have to do there with superconducting qubits, or with ion traps to reach kind of assume 10 million physical qubits operating well. I hope the topological qubit worked out really amazingly well. Let's say first improve your building block. If you go back to the 40s and one builds electronic computers, especially ones with vacuum tubes. It had an error rate of about 10 to the minus 4, 10 to the minus 5. People really had people just switching out vacuum tubes all the time because it broke down and it was not scalable. So the breakthrough came from inventing the transistor. We really have to take the step to basically the transistor of quantum computing. And we need an amazingly good qubit. And then scaling becomes engineering. With what we have now, it feels like I want to build a better scale supercomputer with vacuum tubes. Could maybe do it by building a kind of a boulder size, a boulder city size hall. But I'd rather much better take a rock boulder size machine in with transistors. Because it will really scare me having to build 10,000 logical qubits from Transmon on. If I have to, I'll attempt it. But I first hope for something better. The theory says that it should work out, so let's try it. It's hard, but if it works, then that's clearly the way to go. If somebody else has ideas for another amazing qubit, then please tell me or do it or publish it and build it and show it. I don't care which hardware it is as long as it has 5 or 6 nines fidelity.